Let's go on to problem 4. How many lines intersect 4 given lines in C3 where no 2 of the 4 given lines are parallel or intersecting? Okay, how many think it's A? How many think it's B? And how many think it's C? How many people have no idea? Raise both hands. All right, cool. Great, so this is a lot harder of a question that you probably haven't seen before. So let's imagine it. You have 4 lines in space, and you want to know how many fifth lines pass through all 4 of them. So this is one of the questions that Hermann Schubert was sort of first interested in, these kind of harder questions of intersection. And the way he approached them was to say, I'm looking for an eraser, but I'll just go to the other side of the board. I think they're behind the projector. But, so the way he approached them first is to say, well, let's say in the degenerate case that 2 of my 4 given lines intersect at a point. And then another 2 of my 4 given lines intersect at another point. Well, now the problem's not so hard to solve, because if I want another line that passes through all 4 of them, I can easily just connect these 2 lines, right? Or these 2 points. And now, of course, that red line, I'll just draw it red, passes through all 4 of the yellow lines. And then, is that it? Anybody see other solutions? The one where the planes intersect, right. So you can draw the plane containing these 2 lines and the plane containing these 2 lines. And these 2 planes are going to intersect down here in some other red line. And that red line, since it's in the plane of both these yellow lines, it intersects all 4 of those yellow lines. And that's actually the only 2 solutions you can have in this case. It's not so hard to see. So then Schubert, being back in the 18th century when math wasn't so rigorous, said something like, well, look, it's 2 in this case, and like if you pull apart the lines a little bit by continuity, like there's sort of a principle of conservation of number, and the answer is always going to be 2. And he just sort of claimed it, right? There was a lot of mathematicians who did these problems this way, and they ended up making mistakes for harder problems like number 5. So how many k-dimensional subspaces of C to the n intersect each of k times n minus k subspaces of dimension n minus k non-trivially? I don't know, right? So we'll answer this as the course goes on. So that's, this is one of our goals, is to answer question 5. So this stuff needs to be put on a more rigorous foundation. And actually, Hilbert's 15th problem was to put this sort of method of principle of conservation of number on a rigorous foundation. I also want to point out why I'm working in C here. If I change this to R3, actually sometimes the answer could be 1 or 0. Because basically, this problem itself isn't so hard. You could set up the equations for these lines and try to, figure out what the possible solutions could be for the red lines. You get some quadratic equation, basically, which has 2 solutions over C, but it might have 1 solution over R or something like this. Okay. Okay, so the idea of modern Schubert calculus now is to take the 4 yellow lines. Let's draw them in general position now. So let's take 4 lines. Imagine these in 3 space, so they're crossing each other somehow. Okay, so let's call these L1, L2, L3, and L4. And what we're going to end up doing is making Schubert varieties. Which are defined to be the sets of all lines passing through each of these lines. So we're going to define omega 1, say, to be the set of lines passing through L1. And we're going to see that this has the structure of an algebraic variety. There's a topological structure on omega 1, lots of nice things. And we're going to do the same thing for each of these lines with omega 3 and omega 4. So you imagine all the lines passing through each yellow line, and now if we intersect these sets, then the answer should be in this intersection, right? So we want to compute the size of this intersection, and we want to show it's 2, always, right? So let's do the same thing. Since this concept is so important, let's do the same thing for problem 4. So let's look at point 4 and make it point 4 double prime, where we're going to projectivize and then go up 1 dimension. So problem 4 said, I'm going to get my sheet out here, how many lines intersect 4 given lines in C3? Let me rewrite it here so we can just translate it one step at a time. So how many lines intersect 4 given lines in C3. So let's change this to P3. That's an easy step. We'll make it 0.4 prime. Where no 2 of the 4 given lines are parallel or intersecting. Let's leave that condition for later. Let's just look at what it looks like when we go up 1 dimension. So now we're going to be in C to the 4th. We're actually going to be in 4 dimensions and considering things through the origin. A line, again, becomes a 2-dimensional subspace. So how many 2-dimensional subspaces V intersect each of 4 given 2-dimensional subspaces? So this is in C4. Say V1 through V4. Except we have to be careful about intersect as well. So here, pass through is a little bit funny because everything intersects when you're central, so that can't possibly be the right thing, right? Everything intersects at 0. What is going on is passing through at least a point, or coinciding as lines, corresponds to passing, like the subspaces actually crossing in dimension at least 1. So we have to say such that dimension of V intersect Vi for each I is at least 1. So that's, not something that all 2-dimensional subspaces do in C4. There's enough room for them to just meet in a point, but it's saying that each of them meets in a line or more. Okay, so why did we translate it like this? Well, now we can work in what's called a Grassmannian, which the projective space, the reason I spent so much time on projective space is the Grassmannian is just a generalization of this. So we're going to find the Grassmannian GR of n comma k to be as a set, the set of all k-dimensional subspaces of C to the n. Okay, now I've dropped all pretense of ever working over R. R was just to draw pictures. And now we're going to be working over C for the rest of the course. Okay, so this is very similar to how we defined projective space at first. We defined it to be the set of 1-dimensional subspaces of some other space, right? So in fact, GR of n1 is p to the n minus 1, right? Because we had that other notation. So how do we think of the Grassmannian? Well, we want to put a topology on it like we did for PNs. We want to think of it as a quotient space. So we're going to think of a point as, so a point in the Grassmannian can be represented as the row span of a k by n matrix. Some k by n matrix. So just, k vectors generate a k-dimensional subspace. And then we can ask, what are the relations that we can apply to, we can certainly scale rows and it doesn't change the subspace. Turns out elementary row operations also don't change the subspace, right? Because they're just linear combinations. And so we can basically define it to be the set of all these matrices modded out by elementary row operations. So yeah, let's just define this to be. So it's basically c to the, I don't want to say c to the k times n. I guess I want to say full rank matrices. Oh yeah, these have to be full rank as well to be dimension k. So let's just say full rank k by n matrices, which is some subset of the space of k by n matrices, mod the equivalence relation given by just generated by elementary row operations. So the point is that this, what I want to focus on is the positions of the ones here. I want to think of this actually as just living in a subspace of the Grassmannian whose canonical form, whose row-reduced forms like this, just have this format with the ones there, and then we don't know what these starred entries are. They could be whatever you want. But this is in this set. And this kind of set is called a Schubert cell. We want to associate a partition to a Schubert cell in a unique way. And the way we do that is, notice these positions of the ones is what we're worried about. And we're just going to look at how far they can't be in the same column. So we basically shift them over by one column each and then see how far they are from the left. Another way of saying that is cut out a staircase from the left. Okay, I'm just going to like ignore these zeros over here. And now the distance from the staircase boundary to these ones is going to be the partition that I assigned to this Schubert cell. Okay, so you can almost see the partition. I'm just going to shift it over. So that the so lambda is my 421 here that I assigned to this Schubert cell, and I'm going to write this as omega lambda circle is the Schubert cell corresponding to lambda. And now, finally, we get to define Schubert varieties, which are the same dimension, but they're the closures. So here's the big definition. A Schubert variety which I'm going to write as omega sub lambda with no circle is defined to be the closure of the Schubert cell in the Grassmannian. So now is the exciting part, which we're getting just to at the end. So what is omega box in GR42? Okay, why am I doing this? So going back to the Schubert calculus quiz, that problem that we started with 4 lines in 3 space and lines passing through them, we translated it into an affine problem about 2-dimensional subspaces passing through the origin in 4-dimensional space. So that's why I'm going to consider GR42 now, because we're going to consider 2-dimensional subspaces of C4. And I claim that this Schubert variety is what we need to solve our problems. So let's just write it out with, so this is the partition lambda equals just 1. So it has one part. And using this definition, we can write this as, so this is saying that this Schubert variety is telling us all the 2-dimensional subspaces that intersect a fixed 2-dimensional subspace in dimension at least 1. So that's what we wanted, except we had not just one given subspace, we had 4 different given subspaces. And so we need to somehow change our basis and define a different Schubert variety decomposition of the Grassmannian in order to intersect them and get what we want. So for this, we need what's called a choice of a flag. So it's not just a change of basis. What we really want is a chain of subspaces. So here's the definition. A complete flag in Cn is a chain of subspaces that are all contained in each other. Actually, sometimes 0 is called F0. Let's do that for rotational purposes. Where each dimension goes up by 1 each time. So dimension of F sub I is I. And this is the intersection that we want to show is 0-dimensional and has 2 points for all choices of flag. So let me just now I'm going to skip everything else and go to properties of this cohomology ring for the Grassmannian. So now you're just going to have to believe me what these properties are. Okay, so here's the basic fact we're going to need about the cohomology ring of the Grassmannian. So first of all, this is something that we saw for P2C. Remember, this was the chain complex for P2C, that it had only even degree homology, and it only has even degree cohomology by the same argument, maps from 0 to Z or just 0. So we know, and since the Grassmannian we're working over C as well, has the same exact properties. So non-zero cohomology exists only in even degrees. H2I for some I of the Grassmannian. And what that means also is that, I mean, notice when we took kernel mod image, we basically got the same group as the one we started with, this free abelian group generated by the K cells. And remember, in the Grassmannian, the Schubert cells are our K cells for whatever dimension the Schubert cells are, which means that there should be a basis of the cohomology ring that corresponds to the Schubert cells. And in fact, we call this basis, so there's actually, as a Z algebra, there's generators. So actually, I should just say ring basis over Z basis. I'm going to call it sigma lambda. Now, this is another thing I'm not going to define, but it's called the fundamental class of a Schubert variety, roughly corresponding to that Schubert cell. So this is in actually so we're really taking the dual of a homology class. So the degree it's in is the opposite of its dimension, which is 2 times the size of lambda in the Grassmannian. And then the other very important fact is that the product in the cohomology ring corresponds to intersection of these Schubert varieties. In other words, if we take the product sigma lambda sigma mu for 2 different things, this is the same as the class of the intersection of, you take 2 transverse flags, any 2 transverse flags, and you intersect those Schubert varieties for lambda and mu, and you take its cohomology class. So now this is getting towards a generalization of the Littlewood-Richardson rule. Okay, so we're going to talk about the Littlewood-Richardson rule now. And I better actually put some notation in. From now on, I'll just write LR to write Littlewood-Richardson, so I don't have to write the whole thing out. I might even say LR to save time. So we want to understand something a little more general than the Littlewood-Richardson rule most people are familiar with, because we want to understand the intersections of multiple Schubert varieties. So we want to multiply a whole bunch of Schubert classes for different partitions and see how it expands as a sum of these. So I'm going to call the coefficient C new. And sometimes I'll write, if I have a sequence of partitions like this, which I'm indexing with upper subscripts because I don't want to confuse it with the parts of the partition, then I'm going to just put a bullet to indicate that sequence of partitions, just like we do for flags. OK, so we want to understand these coefficients. And these are this, we know there's the same coefficients as the corresponding expansion of Schur functions now. Sum over nu. And so there's lots of different Littlewood-Richardson rules to actually compute these coefficients. The one that I'm going to do is sort of the classical one in terms of tableaux that have the Yamanouchi property. But there's lots of different, there's things involving Knudsen and Tau's puzzles, and just like things involving Jodot-Decan, which I might get to. But let's just talk about the classical one. So what's a Littlewood-Richardson tableau? So I'm going to just really quickly, we already saw semi-standard Young tableau in Jeff's class, but I'll just say it one more time really quickly because I'm using English notation, so I don't want to confuse rows and columns. So let me just draw one. OK, so here's a skew tableau in English notation where we say it's semi-standard. SSYT is semi-standard Young tableau. If the entries are weakly increasing across rows and strictly increasing down columns. So just flipped upside down from what we're used to. We also say that, so this is skew shape, nu over lambda. Here nu is 653. And lambda is 3,2. And we're going to define its reading word to be the word formed by putting into French notation and then reading the word, which is the easiest way to say it. But otherwise, you have to say you concatenate the rows from bottom to top and left to right. So I like to think, flip it upside down. Now this will be the top row. So we read 1, 3, 4, and then 2, 2, 3, and 1, 1, 1. OK, so this is proof that French notation is better. But again, I apologize for. OK, so then we also need the content of a tableau. So the content is just the vector alpha sub I, where alpha I is the number of i's in the tableau. So for instance, the content of that tableau over there is, how many ones are there? There's 4 1s, 2 3s, 2 2s, and a 4. So the content is 4, what did I say? 2? 2. OK. So notice that this has content that's actually a partition. It's decreasing. And that's something that we're going to need too. So sometimes we call the content mu if it's a partition instead of alpha. And then we say that, so here's the big definition. So the reading word is said to be Yamanouchi, which is also called lattice and also called ballot. So you'll see it all ways. If every suffix has partition content, so every final substring or suffix of the word has partition content, means number of i's is bigger than number of I plus 1s. So one reason it's called lattice is a lattice walk sometimes is like a dick path when you can't have a 2 before you have a 1. If you just have 1s and 2s, this is the number of words for which you'll never outweigh the ones by the twos. So if you're doing up-down walks, you'll never go below the axis. If a 1 is up and a 2 is down, you'll sort of always stay above. So that's the reason it's sometimes called lattice. I'm not sure why it's called ballot, actually. Does anybody know? What's that? Sorry. I was doing prefixes for lattice words, but then I should have written it backwards. So here this word is 1, 2, 1, 1, 2, 2. There we go. So yeah. So what I mean is this prefix has to, suffix has to have more 1s than 2s, and so does this one, and so does this one at every step. But then that has to be true for all pairs, all adjacent pairs of letters, for it to be Yamanuchi. Thanks. Yeah. Yeah, it's very important. Yeah, it can definitely be equal. For instance, 2, 1, I was allowed to put. Yeah.
It's called ballot because you want the number candidate 1 to have at least as many votes as candidate 2, at least as many votes as candidate 3.
Yeah.
At each step of the.
So like a voting system.
Yeah.
Okay, there you go. That's why it's called ballot. Cool. Yeah, so the basic Littlewood-Richardson rule is just for multiplying two shear functions together, so C, we're going to have C lambda with just C nu with two partitions, lambda and mu, is the number of semi-standard Yamanuchi tableau of shape nu over lambda and content mu. So for instance, the one that I wrote here is not Yamanuchi. Can anybody see why? Why is this not Yamanuchi?
3 comes before the 2.
The 3, yeah. So if we read this backwards, 1, 1, 1, 3, I have a 3 before a 2. So that, sorry, this is not good. But I can turn it into a Yamanuchi tableau pretty easily. And let's just do an example where we actually compute a little Richardson coefficient for these shapes and mu being 5, 3, 1, let's say. So you could easily just kind of see how many there are. So the inner shape is still 3, 2. The outer shape is still 3, 3, 3. I guess, sorry, I mean 6, 5, 3. And then to fill it with 5 1s and 3 2s and 1 3, the top row always has to be 1s because it has to start with a 1 in reverse direction. Similarly, this has to end in a 2, just like that 3 couldn't be there. And then this has to be 2 by semi-standardness. We have an ambiguity here. This could be either a 1 or a 2, but we don't know yet. And then we have 1 3. Well, that has to go here because it's a semi-standard tableau. And so then we just have, what do we have left? We have 2 1s and 1 2 left to choose from. So we could either fill it like this or with a 2 down here. And then you just have to check that both of these possibilities still satisfy the ballot condition, and that's true. So that means that in this case, C nu lambda mu is 2. So then the generalized Littlewood-Richardson rule can say that C nu lambda 1 through lambda r is the number of chains of Yamanuchi tableau of contents lambda 1 through lambda r that fill the total shape nu. Okay, so that's going to come in handy now. We can start solving our Schubert calculus problems combinatorially. So now let's actually go to problem 4 on the Schubert calculus quiz that we started with and just compute it. This one's going to be a lot easier than that example. So we had translated the problem of 4 lines in 3 space and how many lines pass through all 4 of them into the intersection problem in the Grassmannian that's in terms of Schubert classes is just the multiplication of 4 single box Schubert classes. And we want to show this is 2 points, right? So we want to show this is 2 times sigma of the whole box. This is something worth remembering is when you have your, so remember we're working in GR 4.2, and the important box is 2 by 2. So the class of the whole box is always just 1 point because the codimension is 0. So we want this Littlewood-Richardson coefficient to be 2. So we want to calculate C box. So here's what we're checking. C box sub 4 little boxes. And so this is the number of ways of filling in a 2 by 2 square with 4 Littlewood-Richardson tableaux of contents 1, right? With a chain of the Yamanuchi tableau of content 1 each. So we really just have 4 different colored ones that we're filling the tableau with. Okay. So my first one has to be in the corner. My second one can be 2 places, right? It can either be here or there. And then the third one is determined because you're extending the shape each time. And then the fourth one is still in the corner. Okay. So there's the 2. Okay. Today I want to go into a very specific Grassmannian that's not the ordinary Grassmannian, which is the orthogonal Grassmannian. And there's a lot of nice combinatorics there and a Littlewood-Richardson rule and everything you might hope for. So let's start on the next variation on the theme of Schubert calculus. And that is, yeah, so we're going to define, so we defined last time the orthogonal Grassmannian of k-planes in, and I'm doing the autoorthogonal Grassmannian here, k-planes in 2n plus 1 dimensional space that are isotropic. I'm going to take the sort of maximal one where you take n planes. And so this was some quotient of SO2n plus 1 by a maximal parabolic. And we thought of it as, yeah, so we think of this as the set of isotropic n-dimensional subspaces V of C to the 2n plus 1. So now we want to compute the cohomology ring H star. So we know this has to be some ring that whose generators are that has a basis indexed by shifted partitions or partitions into distinct parts. And it turns out the right answer is what's called the Schur P functions. These are a type of symmetric function, but they live in a subspace of the symmetric function. So this is going to be a certain quotient of, take the symmetric functions generated by odd degree power sums. So just take P1, P3, P5, and so on like that. And then we're going to quotient by certain things that don't live inside of the important triangle that I'll fill in this later. But essentially, it's the symmetric functions with odd degree power sums. And you can see, I mean, sort of odd degree. There's this theorem, odd degree partitions into odd parts correspond with the partitions into distinct parts. There's lots of different proofs of this fact. So at least dimension-wise, this is sort of the right ring. And then there's something you can do. You can make, so in order to define, so we're going to define these sure P functions, capital P lambda, and that's going to correspond to the homology class of one of our Schubert varieties. And to define P lambda, these are, so I'll write sure P. These are defined pretty similarly to the sure functions, but for shifted tableau. So what's a shifted tableau? So a shifted semi-standard Young tableau is a way of filling, let me just draw one and then I'll define it. Let's see, I want to draw a skew shape. Actually, I'm going to define P for skew shapes, and I can take skew shapes in the shifted case just like we do for the ordinary. We just cut out a skew partition, or we just cut out a shifted partition from another. So let's draw. Okay. So I'm going to cut out this inner shape, and then my shifted partition is going to be, let's say lambda is six, 4, 2, 1, and mu is 3, 2. So this is the shape, the not shaded stuff is lambda over mu. And then I'm going to fill the boxes with letters from an extended alphabet. So now we can have 1' entries as well as 1s, as well as 2 primes, as well as 2s, and so on. And they're ordered so that the primed entries are always thought of as smaller than the unprimed. And they have another rule, which is that, so semi-standard usually means it's weakly increasing across rows, strictly increasing down columns. Well, that's true for the not primed entries. But then we have primed entries too, and those actually have the opposite rule. So I'm allowed to put 2 1' in the same column, but not in the same row. And then, let's see, I have an example here where I have other things going on. But I can put 2 1s in the same row, but not in the same column. Okay. Yeah, so basically, we still have entries are weakly increasing across rows and down columns. And then repeats can be, so primed entries can repeat in columns and unprimed in rows. Okay, so here's the Littlewood-Richardson rule. Well, it's a rule for multiplying sure P functions and expressing them back in a P sure basis. So I'm going to call the coefficients F nu lambda mu. And so F lambda mu nu also equals, if you want, the number of Stanbridge tableaux, let's call them. Of the right shape and content. So I actually, I'm going to shamelessly end with a plug for my own research, which is I've been, me and Jake Levinson, and who's been in the audience sometimes, and Kevin Prabhu are working on things involving the orthogonal Grassmannian, and we needed a better, a different Littlewood-Richardson rule and different crystal operators actually in the shifted case. So we have a different Littlewood-Richardson rule that doesn't involve reading the word backwards and forwards. Yeah, actually, we can actually just read it forwards and know whether it's valid or not. So I'll tell you our alternate rule. This is a paper coming very soon. I think Jake and I are going to try and finish it next week at this conference. So I think. What's that?
So you won't listen to the talk.
I will. It was between the talks, so. The paper has been delayed because I've been preparing for this.
You have long breaks between talks.
Yeah, exactly. So that's how we'll finish it.
If it's good in the archive next slide,
Then you'll know we were paying attention. Yep. All right, so yeah, so here's a little preview. So we can define a lattice walk associated to a reading word. So the walk of the reading word of T is defined as, so actually we're going to define the ith walk as you just look at the, so here we also just looked at the i's and I plus ones. Actually, maybe I should do a quick example of a reading word that has this property. Yeah, so for instance, if you're reading backwards in Stanbridge's rule and you count the number of ones equal number of twos, this guy can't be 2 or 2 prime, right? And then that has to be true when you look at 2s and 3s and 3s and 4s and every adjacent pair of letters. So we also have a similar thing where we look at every adjacent pair of letters at a time. And for the ith walk, I'm gonna write the first walk just to show you how it works. And then it's the same for all the other letters. So you take, look at the subword of 1 prime, 1, 2 prime, and 2. And then we're going to make a lattice walk in the first quadrant where we start at the origin and then we read the word. You know, this subword is going to be W1 to WN or something like this. And if at a certain point we're just out here in space and we want to know what direction we're gonna walk on the lattice grid. What direction do we go? We follow this little compass, which says that if it's a 2, we go up. If it's a 1 prime, we go east. We go south if it's a 1, and we go west if it's a 2 prime. But then we also want our walk to stay in the first quadrant. So when it's on the, if we start at the boundary, if at some point in our walk we're on the boundary, we instead have 1 and 1 prime always going to the right, and 2 and 2 prime always going up. Because we don't want to go left or down. Okay. And then, so let's do an example for... Yeah, that's right. We bend the rules when we're on the boundary, but only then. So, yeah, so for instance, let's look at the word 1, 2, 2 prime, 1, 1 prime, 1, 1. And so we start with the 1, and we're reading left to right now. So we start at the origin, and a 1 goes to the right when it's on the boundary, which the origin is. And then a 2 always goes up, no matter whether we're on the boundary or not. 2 prime, now we're off the boundary, so we follow our compass, and we go left. And a 1, we're on the boundary, so where does a 1 go? 1 goes to the right. So we actually get, let me label this down here, we actually get back here to this same point with our 1. So we've done this so far. Now we're at 1 prime. 1 prime always goes to the right. And 1 goes down if we're off the boundary, like that. Here's our 1. And then now if we're on the boundary, 1 goes to the right. Because we don't want to end up down here. So, okay, so there's the walk. And so the theorem is that we have our reading word is Littlewood-Richardson or Stanbridge or whatever you want to call it. So I'll just call it Littlewood-Richardson, the Littlewood-Richardson tableau, if and only if each of these walks ends on the x-axis. The ith walk end on the x-axis. Okay, so that's the condition, and so it's a much faster condition. You just read the word left to right, you draw out your walk, you see where you end, and there you are. So.
What's the ith walk?
This is the 1 and 2 walk. The ith walk is for i's and I plus 1s. So you draw all the walks for each of those. We were trying to actually, I mean, we were hoping that we could do like an n-dimensional walk where you just do 1s and 2s and 3s in all different directions. But actually, it doesn't seem like you can glue them together in any easy way. I mean, there might be something that we haven't found yet, but that would be certainly worth investigating. Yeah.
Are any other statistics of these walks coming up, like how far you go on the x-axis?
Absolutely, yeah. So actually we have a whole general theory that's not just these walks that end on the x-axis. If you end up out here, if you have x comma y as your endpoint, then that tells you pretty much everything about the rectification of that strip. So if you just take the 1s and 2s and you're asking, what does the rectification look like? Well, there's not actually that many things that a rectification of a word of 1s and 2s can look like. There can't be, because there can't be any primes on the diagonal or in the start. So the only ambiguity, like once you know the shape and the content, the only ambiguity is whether this 2 is primed or not. And actually, up to that priming, this x comma y uniquely determines the shape and how it's filled, the content. And you don't even have to look at the rest of the walk moves. Like you don't have to know how many 1s and 2s you had in advance. You know just from the endpoint. And we actually, so as a preview of what our work is going to be, we have crystal raising and lowering operators that change the weight of our word by 1 each time. And the raising and lower operators basically move the endpoint either up and left or down and right. So that's why when it ends on the x-axis, basically that means our raising operators ended and we can't raise it anymore. Except, I mean, I want to have a caveat that we have a very complicated, it's not like a standard crystal. We have this sort of doubled crystal that has 2 types of operators and we need to combine them. But they all do this to the endpoint of the walk. So the walk ended up being super useful in understanding like almost everything about the tableau, and I think it's going to end up being more useful in the future.